design verification engineer for General Dynamics Mission Systems. He holds a BS and an MS in electrical and computer engineering from the University of Florida. Mark is passionate about developing new and innovative techniques to solve common verification problems across all applications. The title of his paper is Adapting the UVM Register Abstraction Layer for Burst Access.
How do I start this next one? Oh. Okay, where's the
Wayne, how did you advance slides? Which one? Big arrow.
Okay. All right. My name is Mark Wilpondo, verification engineer with General Dynamics. For the past year, I've explored the UVM register abstraction layer in my verification environments, looked at some of the advantages and disadvantages of it, and as well as some limitations. And so, the paper today I'm going to talk about is one of the limitations in regards to front door burst access using the register abstraction layer. Okay. So a brief background of the UVM register abstraction layer, for those who are not familiar with it, it's the standard method to model your DUT's registers and memories in your UVM environment. So it provides a set of base classes like this UVM_reg, which allows you to model one for one the registers in the DUT in your UVM environment. So it has a powerful API where this UVM reg has a number of built-in methods that the task or sequence writer can use to manipulate the DUT and the register model itself. It uses passive and active mirroring, and what that means is that passive mirroring is where it will monitor all the transactions on the bus, on the configuration bus, and it will update the register model for any transactions it sees on there. Active mirroring is less commonly used, and that just means that when we create a sequence, a write sequence, it will update the register model based on our test rather than what it sees on the bus. So it's a very powerful tool in UVM. This paper is not going to go into detail on how to hook it up or how to use the register abstraction layer. There are a lot of tutorials on that, so I encourage you to check that out if that's what you're looking for. So moving on, we have the single axis problem. So in a lot of my tests that I write, I like to mimic how the design is going to function in the real world, how is software going to program the hardware, right? So by doing that, I like to use the front door access method, and that just means we're actually manipulating the configuration bus to configure our register space. Okay, so this is the standard way to use the abstraction layer to configure a certain register. We create our status, our single value write data. We set that write data, and we call this reg.write function. This is the register name in our register model, and this is our register block. And so we pass in the write data our abstraction layer, our register adapter is going to take that and convert it to a bus sequence item, which will drive our configuration bus. Okay, so that's how we do it right now. Single access. Notice we can only input one value into this function. Okay, so only supports single access. So if we want to write multiple registers, well, we have to do multiple write. We have to call multiple write methods for each register. So this would write to 3 different registers with 3 different data values. And so it can be kind of cumbersome if you have a register, if you have thousands of registers in the design and you have to configure them all. You're going to have to call this write for each one, and it's very cumbersome when you're writing these sequences to do that. So is there a better way? You know, can we write multiple registers at once? Let's find out. Okay, so this is the bus protocol that I use, that's described in the paper as the example. It's a very simple protocol. We have a frame which signifies, you know, the start of a bus operation. We feed it a read write followed by a start address, and then we just burst the data through here with the val. So this is kind of a master-slave setup where the master will start the bus operation, and this data bus is shared between the master and slave. So the slave can communicate on that data bus if we're doing a read and can provide the read data. Don't worry too much about this protocol because the solution here is not dependent on the protocol at all. As long as you have a BFM that can, you know, drive whatever protocol that configures your registers, the method should work for that as well. This is just the protocol that I used. So this is the goal. This is what I want to create. I want to create a bus transaction that looks like this from using the UVM register layer. So I'm going to take you through my thought process about how to do that. And so I mentioned before, you know, if you want to configure multiple registers, we're going to have to call multiple write commands. So maybe I can call multiple write commands. You know, let's see what that does. Maybe it'll look something like that. I don't know. Well, it turns out that when we call something like this, what it's going to produce on the interface side is that it's going to call something that I name multiple single axis, where it's basically creating multiple bus operations which only write one data word at a time. And so you can see this is definitely not equivalent. This is not what I'm looking for. I want to program our register space the same way software is going to program our register space by bursting the data. And this solution is definitely not the same. And this is a much more inefficient solution when it comes to simulation. So what's next? What are we going to do here? Since this write doesn't work, what can we do? Well, if you're familiar with the UVM register layer, you probably know about the UVM mem class that it provides. This is similar to the UVM register class, except it's for modeling memories. Now, UVM mem actually has a built-in method called burst write or burst read. So it has it built in, so why can't we just model our registers as UVM mem types and then call it burst write and burst read, and that should work, right? Well, the answer is no, because the problem with that is that the UVM mem class is not actually mirrored in our environment. So what that means is our environment, it's more of a placeholder in our register model. It's not actually mirroring the values of the DUT. It doesn't maintain the values. And so that's pretty much useless to me because I can write sequences that just create this without the register abstraction layer, and it'll accomplish the same thing, right? Because isn't this, if I write a sequence that does this, it's not mirroring any values either that come across the bus. So UVMN not work as a solution. So what else can we do? We can adapt. Okay, so part of the functionality of this write function and the read function is the ability to pass what's called an extension object into the method. The extension object is just a UVM object that's user defined, so you can pass anything into it. So maybe we can use this extension object to create a burst operation. Okay. So the extension object. So this is an example of what my extension object looks like. It's just extends from UVM object. You can literally put anything you want in here that you want to transfer to the register adapter. So I put some transmit place and device ID. Just based on the protocol, I can add constraints in there. It's fine. The real key here is this burst data. So the idea here is to, instead of transmitting our single data value through our UVM reg.write or read, we will store all of our burst data inside this extension object and then pass it to the register adapter. So I like to use system_IQ here for my burst data, just because I like using the queue functions. But if you don't have to use a queue, you can use any kind of data type you want. It doesn't matter. As long as you're able to decode it at the register adapter layer, you can use anything you want to store your burst data. And also this is also relevant in that you don't have to have the same configuration bus or the same bus protocol. Whatever your protocol needs, that's what you're going to put inside your extension object, because when you get to the sequence item, the bus sequence item, you're going to use that information. Okay. So we create our extension object. We move on to the register adapter. Now, if you're not familiar with the register adapter, it has two virtual functions that the user is required to override in standard procedure, right? So anyone who uses the UVM RAL needs to override these functions, and one of them is called reg to bus, and the other one is called bus to reg. And so the idea here, reg to bus will take the register sequence items and turn them into bus sequence items, and the bus to reg function will take the bus sequence items and change them into register sequence items. So here, all I need to worry about is the reg to bus, just because I'm passing in the extension object, doing a burst write. So all I have to do here is transcribe my burst data from I grab my register item here, I grab its extension object, okay, and all I have to do is transcribe that extension object burst data into my bus sequence item. So as long as you have a BFM that can handle a bus sequence item and can drive that data, you're able to, it'll receive its data from the extension object itself, instead of this reg bus operation. That's normally what would provide the data that you want to drive into the bus. So this is an example of reg to bus. Now this is not modifying any UVM code or anything. This is just any UVM library code. This is you have to create something like this if you want it to work by normal operation. So it returns our bus transaction or bus sequence item, and that can be picked up by the sequencer and the driver. I didn't include the bus to reg function here because there's nothing different that you need to do for bus to reg outside of normal operation. I'll go into how we collect the first item next. So we're done, right? We created our extension object. We can drive burst data into the bus. Our BFM can handle that and stimulate the design. So that's all we need to do. That's not true because we forgot about the other path from the actual bus, converting that back into a register sequence item, and then updating our register model. So the second part of the solution has to do with the monitor. Now this monitor will sit on our configuration bus, it's going to gather, it's going to see that burst transaction. And now, don't worry too much about this code here. This is in the paper if you want to look at it, but focus on this burst data. It will receive it will be looking on the bus. It'll see that, hey, I've got an operation that bursts 3, 5, 100 different registers. So I have to somehow translate this into something that the register predictor can understand. Now the register predictor, there are no functions you can override there. It's not recommended. I don't want to change the code of the register predictor. So it can only understand single access. So in order to solve that, we need to take our first access sequence item and convert it to single access sequence items before we publish it on the analysis port. Okay, so this function is essentially doing that in our monitor. We gather our burst sequence item and convert it to single access sequence items. We publish on the port, and as long as you keep publishing them on the analysis port, the register predictor is going to pick up everything it sees there, and it's going to update the register model. So that's all you have to do for the monitor. Okay. So bringing it all together, let's just talk about UVM reg burst write. What we start with. So we start with our extension object. This contains our queue of burst data. Okay. We define this in a test or sequence. We pass in our extension object through our UVM reg.write command. That is forwarded to the register adapter. In the register adapter, we transcribe our extension object into a bus sequence item using the reg to bus function. That passes the sequencer into our driver, which driver uses our BFM to create a burst write that uses our protocol here. Okay, that stimulates the DUT. We've done the burst write to the DUT. Now our monitor is also sitting on the same bus. It sees the burst write, and since we want to keep a mirror of the register values, it will pick that up. It will convert the burst write into single writes, single access. That will go to the register predictor, which will then update the register model because the register predictor can actually digest the single writes as opposed to the burst writes. So that's the whole path that it's going to go through using this extension object. Okay, so here's a test case that kind of looks like in a code point of view, same kind of thing. I skipped, build phase, everything like that. We're just extending from UVM test here. What we do is we create our extension object. We fill in the appropriate extension object values, and so your solution is going to look different than my solution because if you have a different bus protocol, you might need to feed it other information in order for it to properly join. So here's our burst data here. I just formed burst data here. I call our write, and I pass in the extension object. Okay. Now I'm passing in 16 hex 0 here. That's normally where the data goes that you want to write. That's normally where it goes. It doesn't matter what you put here. You can put any value here. It doesn't matter because our reg to bus function in the register adapter is doing nothing with this data anymore. It's taking all the data from the extension object, so that's the only important part right now. So this is not important. Now, what may be a little confusing when you're writing these is that my bus protocol automatically increments the address as it writes. So if yours does something different, if your burst does something different, you may need to take that into account because I give it the starting address here. This register is the starting address. That's the name of the register, but its location is the starting address. So I give it that, and then I'm going to burst through reg 0, reg 1, reg 2. Okay. So if your protocol has a different burst format, you may need to take that into account. Which one you're actually calling with the write and read on. Okay. So that's our test. Okay, so this is not a perfect solution. There are some limitations with it, just because it's workaround. It's not officially supported, by UVM. So there are limitations with this. The first one is not really a limitation, but more of a requirement. You have to create the extension object, and you you have to pass that in as in the right engine commands. The second one is a pretty big deal because it's unfortunate, but if you're doing a read, a burst read, it won't return the data values back to the tested sequence. And that's just because the register predictor doesn't know anything about burst. So it can't return multiple values. It's just the function, the read function can't return multiple values, and you can't do a backwards extension object, back into the register model. It doesn't work. So if you're doing a read, a burst read, your model's going to be updated correctly. It's going to be updated correctly because we're splitting that up into single axis, but the actual function, the actual read function will not return a queue of red data. So that's one limitation. Third one, the UVM reg mirror front door method isn't supported. So this is similar to the UVM reg read. I really like this function because it does an automatic compare. When it sees, when it does a read on the bus, it'll do a compare with your model to make sure that those are the same values, or else it'll flag an error where you have UVM check here. That's not supported because it has no knowledge of the burst read. So there might be more limitations. These are just three that I noticed right away. Okay. So the summary. So this is a consistent, easy method for exercising the burst protocol bus. You don't have to change the UVM library components at all. That's a pretty big thing for me. I'm glad I didn't have to do that. Didn't want to do that. So you don't need any custom methods for driving burst as opposed to single axis. You can use the UVM reg write for both of them now. Okay. Normal operation is unaffected, meaning if you want to just do single axis, you can just do that. Nothing in the UVM register that has changed, the model has changed. Everything should work the way it has before. So the other really big advantage of this is that the extension object can support multiple purposes. So even if you're not interested in burst writing or reading, you can use the extension object for anything you want. Any information that the registered, the bus sequence item is going to need, you can put in that extension object. So you can use it for anything you want because it's your own class. This little triangle here is if I were selling off this method, you're going to increase your functional coverage just because we're actually covering the burst protocol now. Or if we're just using UVM reg write, it's not creating that burst functionality, so we're not going to hit that coverage. It increases the speed just because we can take advantage of what the design was actually meant to do. That is, burst data burst is obviously going to be faster than the single axis, and in simulation that's true too. Simplicity, I like this because now I can, when I write my sequence, I can just use UVM reg write for all of my configuration. I don't have to use other custom methods that I write, and I know that this will keep the register model in sync with it. Okay, so some recommendations for the UVM library. It doesn't really make sense for the burst, if they were to add a burst write, burst read, it doesn't really make sense for them to add it to the UVM register, UVM reg class, UVM underscore reg, just because the methods there should be, the scope of those methods should only be for that register. So if you're doing a burst across multiple registers, it shouldn't have the ability to do that really. If I were to add a burst axis method, it would be in the regmat class or the reg block class, because they have information of all the registers in your model, and so they can properly burst through them. That method shouldn't produce multiple single axis operations, so that already exists in the regmat class. It has something called a bus write, I think, where you can actually create multiple single axis operations using that. And it should return multiple data words from a single operation that would help with the reading. If this is implemented, the UVM reg predictor will have to be updated because it has no knowledge of burst right now. Okay, so that's it. Questions?
Thanks for a very clear presentation. I was messing around with this stuff the other day and did manage to use the extension object to pass the response transaction back up to the corner.
Oh, did you?
But I had to use a front door sequence rather than the adapter. So you
Okay.
might like to have a play with that.
Yeah.
So if you use the front door sequence, you can extract all your burst data, stick it in the extension object, and send it back up to the read.
Interesting.
But you have to create the extension object before you call the read.
Okay.
So the read isn't generating the extension object. You give it an extension object, and then your front door sequence can populate it.
Oh, okay.
So you might like to have a go at that. But great presentation.
Sure. Thanks. Thanks for the input.
You recommended implementing the rag map class sheet and burst. Why you didn't go ahead and implement it and propose it as to be included in the UVM standard, for example?
Well, one of my goals is not to mess around with the UVM code, but I guess that's the next step, right? Let's update the register predictor for and the methods within each of those classes to support this. But that wasn't my goal in the end. Okay. Any more questions?
Yeah, I have one.
This is a very nice presentation, thank you. But I actually was wondering whether you actually thought about extending the reg block class and putting the block read and write into that class instead. Because part of the problem is that you could have bubbles in your register space,
Sure.
and you don't quite address that part of it. And I was
Right.
wondering if you knew or had thought about that limitation.
Right, so that's the next step too, is if we're actually want to put a real method in and not just use the workaround, it would definitely have to be in that reg block class because it has knowledge of the whole register, whole address space, right? So,
The other question I had was on your previous slide, you were talking about the fact that the data cannot return to the sequencer, to the sequence. And I probably missed the context on that one, but I was just wondering if you had a monitor in the agent that was feeding the data back, you could have basically propagated the data back to the sequence, and I was just trying to understand.
yeah, you can propagate the data back, but once it gets to the register predictor, and it won't be able to come back into the test that called the read, for instance.
Okay. Third question, and probably the final one, is have you looked at this in terms of the effects on the write one, read one clears and the others? Did you have any of those kinds of registers in your design?
I have not looked at that.
Thank you.